Welcome back everyone. In this lecture, we will actually prove Burnside's theorem using representation theory. So, like I said, Burnside theorem actually stated in a different way using solubility. So, let me not get into that. So, I am going to state it slightly different. So, here is the statement. So, Burnside's theorem actually asserts that any group of order p power a q power b with p and q are primes. So, that is not simple unless it is cyclic of prime order. So, let us take the group which has order p power a q power b with p and q are primes. So, then we can conclude that G is not simple unless it is cyclic of prime order. So, we all know that the group of order P is prime, that is cyclic and it is simple. Simple means it does not have any non-trivial normal subgroup. So, let me just recall here. So, G is said to be simple if G has no non-trivial normal subgroup. Okay, so, that is the definition of simple. So, we are claiming that if you know that the group has order p power a and q power b, where p and q are prime, then it is not simple unless the group has order exactly p. Okay, so, this is what we want to prove ultimately, but to prove this we need to actually make some preparations. So, the very first thing that we need to actually prove is that so the following proportion. So, from this proportion we can actually conclude Burnside's theorem easily. So, let me first state this proportion and then see the proof of Burnside's theorem using it, and later we will actually prove this proportion, which actually requires some more work. So, the proportion asserts that whenever you take a finite non-abelian group and assuming that it has actually a conjugacy class. So, suppose G has a conjugacy class C which is different from the identity such that the cardinality of C is let us say prime power for some t greater than or equal to 0. So, then we can actually conclude that this is G is not simple, then G is not simple. Okay. So, when t equal to 0, so it is note that when t equal to 0, then the cardinality of C is 1. That means the number of elements in the conjugacy class is going to be exactly equal to 1. So, that would imply that. So, let us say G is the element that is there in this conjugacy class, then this C is G, and that would imply that this element G belongs to the center. Okay. So, that would imply that the center is non-trivial. So, that means you have actually non-trivial normal subgroup of G, because we already know that the center must be always normal subgroup, and since G being non-abelian, so the center must be proper inside G, and this actually tells it is non-trivial. So, it is a non-trivial proper normal subgroup of G. So, that means G is not simple. So, for this purpose like we can just assume that this t is bigger than 1, but anyway, so this is some simple observation. So now let us actually use this proportion to prove Burnside's theorem. So let us actually see the proof of Burnside's theorem. So which just asserts any group of order p power a q power b. So that is not simple unless it is cyclic of prime order. So if it is cyclic of prime order, then we already know it is simple. So those cases we can just ignore. So that means if we take order of G is p power a q power b, we can assume that we do not have this a b is not equal to either 0 1 or 1 comma 0. So again it is not going to be 0 comma 0 because it is a non-trivial group that we can actually assume from the beginning. So maybe let me state this fact, this is very important fact. If you start with an abelian group, finite abelian group, if it is simple, if and only if, so it is cyclic of prime order. Actually we do not need this finite condition. So because of that, like if G is abelian and of order p power a q power b, then that would imply immediately that it is cyclic of prime order. So we can make this assumption because of this fact G is non-abelian. So without loss of generality we can assume that G is non-abelian. If it is abelian, so then you can actually see that the only abelian simple groups are cyclic of prime order. So we have our observation. So because of that we are going to assume that it is non-abelian. So now for some reason let us say one of A or B is 0, then what happens? Then it is actually a P group. So suppose A is 0 or B is 0. So then we know that G is a P group. So P group means it is of order prime power. Then we already know that for any P group the center of G must be non-trivial. So that would imply that the center of G is proper normal subgroup inside G, proper non-trivial normal subgroup inside G. So that would say that G is not simple. So for P groups we already know the result. So because of this we can actually simply assume that both A, B are actually greater than or equal to 1. So we can assume that both A, B are greater than or equal to 1. So we have order of G which is p power a q power b and both A, B are greater than or equal to 1. So now what we can do, we can actually take this H which is subgroup of G. So this actually comes from Sylow's theorem. So using Sylow's theorem we can actually get a subgroup H of G such that the order of H is exactly q power b. So now what we are going to do, we are going to actually take some non-trivial element in the center of this H. So since the H is P group, so that would imply that the center of H must be non-trivial. So now what we can do, we can take G which is not identity from the center of H. Okay. So we have the center which is sitting inside H which is sitting inside G, and this has order q power b and this has order p power a, q power b, and this is going to have order some q power, let us say s, or yeah. So, now we have this G which is in the center. So, now we fix this and then look at the normalizer. So, consider the normalizer of this element. So, this is going to be a subgroup inside G. So, those x in G such that it just normalizes this one element G, basically it is centralizer. So, x G equal to G x. So, this is same as the centralizer and this is a subgroup inside G. So, since G is coming from the center of H, that would imply that H is a subgroup of this normalizer of small g. So, we have H which is a subgroup of the normalizer, and we can easily see that what will be the order of the quotient G modulo n g g. So, order of this is going to be order of G divided by the order of n g g. Now, since H is subgroup of n g g, that would imply that actually this q power b divides the order of n g g. Now, since order of G is equal to order of G divided by the order of n g g times the order of n g g, and this part is actually divisible by q power b, that forces that this ratio must be some some p power. So, this is going to be must be p power t with t greater than or equal to 0. But what is this number exactly? So, if we go back to the conjugacy action of G and then look at the number of elements in the conjugacy class of G. So, then we can know that the number of elements that are conjugate to G. So, which is exactly the cardinality of the conjugacy class, which is given by exactly the cardinality of G divided by the cardinality of the centralizer or the normalizer of G. So, this is exactly the cardinality of G divided by cardinality of n g g, which is exactly p power t with t greater than or equal to 0. So, that means we have produced an element whose conjugacy class has exactly order p power t. So, then we can actually go back to our proportion that I stated before. So, once you have a finite non-abelian group and that has a conjugacy class different from identity and whose cardinality is p power t. So, then we know that this group must be not simple. So, then from this we immediately conclude that the group is not simple. So, from here we conclude that G is not simple. Okay. So, this actually tells us that the only thing that we need to prove is the proportion. So, to prove the proportion we need to actually prove another important theorem. So, maybe let me state that theorem and then later I am going to prove this theorem. So, this theorem actually asserts something about the irreducible representations. So, what we do, we just fix a finite group of let us say order n. So, then let us fix one conjugacy class. So, we say that H is the cardinality of that conjugacy class, and we also fix one irreducible representation of this G. So, this is irreducible representation. So, with these notations, so we have the following important assertion. So, suppose that the degree of this representation is actually relatively prime to the number of elements in this conjugacy class. So, that means GCD of D comma H is 1. So, then we have the following: either we can say that there exists lambda in C cross such that all the actions phi g that is given by lambda times identity for all G in C, or we can conclude that the character value on G is going to be 0 for all G in C. So, now note that so the character value is actually going to be constant on entire capital C. So, if we know that there exists some element G in C such that chi G is 0, then we can conclude 2. Similarly, for 1 you can see that if phi G is lambda times identity for some G, then that would imply that phi G is going to be same lambda times identity for all G in G, because all elements of C they are a conjugate. So, here is the note: suppose phi G is lambda times identity for some G in C, since the conjugation of scalar matrix going to preserve the scalar matrix. So, A lambda I, A inverse is going to be lambda I for all A invertible matrix. So, because of that you can see that this would imply that phi G dash equal to lambda times I for all G dash in C. And similarly, you can also see if chi phi of G is 0 for some G in C, since chi phi is class function. So, we get chi phi of G dash is 0 for all G dash in C. So, with this assumption you can actually reduce to the case that it suffices to show that if phi G is not equal to lambda times identity for some G in C, then chi phi of G is 0. So, it suffices to show that if phi G is not equal to lambda times identity for some G in C. So, then we conclude chi phi of G is 0. So, this is what we are going to prove ultimately. But anyway, so like I said, I am going to prove this later. So, we will see the proof later, later. So, first what I am going to do, I am going to actually prove the proportion that I promised before. So, we will just prove this proportion and then using this theorem. So, then later we will actually prove the theorem. Okay. So, how are we going to actually prove the proportion? So, what we want to prove? So, we take a finite non-abelian group that has a conjugacy class different from identity whose cardinality is p power t for some t greater than or equal to 0. Then we claim that G is actually not simple. So, let us actually fix a non-abelian group satisfying those properties. So, proof of the proportion. So, we want to prove actually G is not simple. So, we can just go by contradiction. So, assume that G is simple. So, assume that G is simple, and we are actually fix these notations. Let us call phi 1 etcetera phi s. So, this is the complete set of representatives of equivalence classes of irreducible representations. So, this irreducible representations of G, and then whose degree is given by d1 etcetera d is. So, degrees of these representations. Now, we can also call chi 1 etcetera chi s to be their characters. Okay, so, this is the notation that I am going to use. So, now we actually fix this phi of 1 as before to be the trivial one dimensional. So, this is trivial one dimensional representation, in particularly d 1 is 1. So, with this notation you can see that since G is simple, so we must have the kernel of all this p k phi k that is going to be trivial for all k greater than 1. So, kernel of phi 1, since phi 1 is trivial homomorphism. So, that is going to be exactly G, but for all other k greater than 1 the kernel, because it is a normal subgroup and we assume that G is simple. So, we must have this kernel to be trivial. So, that means this phi of k is indeed injective map. So, phi of k is injective for all k greater than 1, and note that this C cross is abelian, and we have this G non-abelian because we started with the G finite non-abelian group and we assumed it is simple, and G is abelian, that would implies that plus phi of k is injective. So, this would imply that phi of k are not one dimensional representations. So, that means d k is greater than 1 for all k greater than 1. So, this is what we have. So, now we can also see that G is simple plus non-abelian. So, that would imply the center should be trivial. If center is non-trivial, then it will be full. So, that would actually tell us that it is indeed trivial. Okay. So, we have all these facts. So, now what we will do, we will actually start by fixing some element G in C, and then we also take k which is greater than 1. So, we are going to actually look at the set of all elements x in G that is going to act as scalar matrix. So, let us call Z k. So, this is set of x in G such that phi x k. So, the kth irreducible representation, that is what we are looking at. So, this is a scalar matrix. So, this is the set that we are interested in. Now, note that if we take this capital H, which is all possible scalar matrices, and that is indeed a subgroup of GLDKC, and that is actually the center, that is actually normal subgroup. So, this lambda identity dk. So, where lambda in C star. So, this is normal subgroup inside GLDK of C, because this is the center. So, this is the center of GLDK. So, now you can see that because this is the center, Zk is nothing but the inverse image of H under this phi k. So, that means Zk is also a normal subgroup of G. So, phi k inverse image of H is going to be Zk. So, that implies this is normal subgroup inside our group G. But since G is simple, so since G is simple, so that would imply that Zk is trivial, otherwise it has to be full. that would make that G is abelian. So, we have Zk, all of them are actually trivial. So, we have Zk trivial, which is nothing but all possible elements in G such that phi k x acts as a scalar. So, this is we have from the simplicity of G. So, now for the moment let us assume P does not divide dk. So, then from our previous theorem we can conclude that chi k of G must be 0, because let us go back to our previous theorem. So, whenever you have a finite group of order n such that the order the degree of the representation and the order of the conjugacy class, they are relatively prime. So, then we can either have phi g to be scalar times identity for all G in C, or we should have this the character value on G must be 0. So, now what we have here in our situation, that the only element that acts as scalar is just a trivial element. So, that means if we take this G from your conjugacy class. So, this is actually we can take it to be non-trivial element. So, then you can see that if P does not divide dk, so then the GCD of this P and dk, so that is going to be exactly 1. The cardinality of C and the degree of the representation, the GCD of this is supposed to be 1. So, let us go back to the statement of the proportion. The proportion actually tells us that the conjugacy class exactly has order p power t. Okay. So, because of that we can actually conclude since P does not divide dk, the GCD of this cardinality of C and dk, that is supposed to be 1, they are relatively prime. So, that is why you get this chi k of G is 0. So, now using this what we can do, we can actually take L to be the regular representation of G. Now, we can decompose L into some d 1 times phi 1 direct sum etcetera direct sum ds phi s. So, we already proved that the multiplicity of phi I is supposed to be exactly the degree of that phi I. So, which is d I. So, this is something we already proved. So, since the regular representation is decomposed like this, we can conclude that this G, because this is non-identity element. So, from this we can conclude that the character value of this G is for the regular representation is going to be 0. Now, that is exactly given by this d 1 chi 1 of G plus etcetera plus ds chi s of G. So, this is because chi L is nothing but d 1 chi 1 plus etcetera plus ds chi s. So, now you can see that whenever P does not divide dk, we have chi k of G is 0. So, using this we conclude 0 equal to so d 1 is 1. So, we keep 1 separately plus summation k runs over from 2 to s such that where P divides dk and dk chi k G. So, this is what we get, because whenever P does not divide dk, then chi k of G is 0. So, you get exactly this. So, now if you simplify this, this would imply that 1 plus P times Z is equal to 0, because we can just multiply by p here and then divide by p here. So, then you get exactly take out the p, the sum of these elements. But then it is noted before that, if you take the character chi of g is not supposed to be algebraic number, because that is nothing but a sum of some nth roots of unity. So, since chi k of g is an algebraic number, so that would imply that this z is also an algebraic number. So, because this z is nothing but integral linear combination of chi k of g. So, we have this z which is an algebraic integer. So, now you can see that z is nothing but minus 1 by p, which is an algebraic integer, which is also a rational number. So, this is belongs to q. So, q intersection a, we already noted that that is nothing but set of integers. So, basically this actually gives us z equal to minus 1 by p, which is inside z, the set of integers, which is a intersection q, which is a contradiction, because minus 1 by p for prime p, it cannot be an integer. So, that way we are actually getting a contradiction by assuming that g is simple at the first place. So, that means our assumption on g that being simple is not correct. So, from this we conclude that g is not simple. So, okay, this actually kind of completes the proportion that I promised, still modulo the theorem that we are supposed to prove. So, I will give proof of that theorem in the next class, and with that theorem proof, we are actually done with the proof of Burnside's theorem. Okay, I will stop here. We will continue in the next class. Thank you.